Welcome back everybody to MIA 270 or Material Science. This is your first tutorial session and today we're going to be dealing with mechanics of materials. So let's move on to problem 1. Problem 1 says, consider a cylindrical steel alloy specimen which is being pulled in tension, having a 10 millimeter diameter and an initial length of 75 millimeters. The stress strain curve for the steel alloy is shown down here below. Part A says calculate the modulus elasticity or the Young's modulus using the stress strain curve. And part B says determine the specimen's elongation when a load of 23,500 newtons is applied. So as we can see from this graph, it's a very typical stress strain curve for the steel alloy. We have a clearly defined point of linear elastic region, a predominant point of yielding, and then a crescendo all the way down to a point of fracture. So it's important to note that past the point of yielding, we have plastic deformation. So the problem asks us to find Young's modulus. So Young's modulus is defined as the slope of the linear elastic region. So what we need to do is write down our slope equation and then plug in the values of anything before the point of yielding, and that's how we're going to determine Young's modulus. So let's first define the point of yielding. We can see that the part or component of this steel alloy starts to yield right here. So any value below this yield stress, we can take and calculate our Young's modulus. So our Young's modulus is defined as our change in stress over our change in strain. So that's equal to a stress at point 2 minus a stress at point 1 divided by the strain at point 2 minus the strain at point 1. So let's just select our values. So let's take 400 megapascals as our applied stress and go down and get a strain of 0.002. Let's also take 200 megapascals as our first applied stress and come down and get 0.001. So substituting those values into our equation, we'll get 400 megapascals minus 200 megapascals divided by 0.002 minus 0.001. This is going to yield a value of approximately 200 gigapascals. So now you're probably going to ask, why did I not write a unit next to the strain? And that's because strain is unitless. However, you may see it in some textbooks as inch per inch or meter per meter. But it doesn't matter because that still means unitless. Now let's move on to part 2. So part 2 of the problem, or part B, says determine the specimen's elongation when a load of 23,500 newtons is applied. So we already have our Young's modulus, which we calculated in part A. So now we need to write down our 3 fundamental equations which govern our mechanics of materials. And those are, our stress is equal to force divided by the cross-sectional area that it's being applied to. The second is our strain equation, which is equal to our change in length over our initial length. And this change in length is often referred to as elongation. And our final of the 3 equations is Hooke's law. And that relates the applied stress to the induced strain. So Hooke's law states that the stress applied to any cross-section is equal to the induced strain times Young's modulus, so long as the deformation is elastic. So that is before the point of yielding. So using these 3 equations, we can manipulate them and solve for our unknown, which is our elongation. So we're going to do that as follows. So we're going to say our elongation is equal to our strain times our initial length. And then we're going to substitute our strain using Hooke's law as stress divided by the Young's modulus. We're going to further manipulate for the stress as force over area as follows. So we're going to change this to force divided by our area times our Young's modulus times our initial length is still equal to our elongation. Now the final thing we need to do is define our area. So the problem says we're dealing with a cylindrical steel alloy. So we know that our cylindrical specimen will have a circular cross-section defined by or governed by our radius. So our area for a circle is going to be pi d squared over 4. So we can substitute that as force over pi d squared over 4 times our Young's modulus times our initial length, and that's going to give us our elongation. So let's substitute our values and determine our result. So our change in length, or our elongation, is equal to our applied force, which is 23,500 newtons, times our initial length, which is 75 millimeters, divided by pi, our diameter, which is 0.01 squared, and that's in meters, divided by 4, times our Young's modulus, which is 200 times 10 to the 9 pascals. Now, we want to be consistent with all of our units. So that's newtons, meters, and pascals. So what we should do is change this value here to 0.075 meters. And that's going to yield a result in meters as well, and then you can convert that to millimeters. So that's going to equal approximately 1.122 times 10 to the minus 4 meters, or we can simply write our elongation is equal to, or approximately equal to, 0.11 millimeters. And that will be the final answer to part B of question 1. Let's move on to problem 2. So problem 2 says a cylindrical specimen of a hypothetical metal alloy is stressed in compression. If its original and final diameters are 20 and 20.025 millimeters respectively, and its final length is 74.96 millimeters, compute its original length if the deformation is totally elastic. The elastic and shear moduli for this alloy are 105 gigapascals and 39.7 gigapascals respectively. So this is again a very fundamental problem. And this problem is trying to teach us to do is relate the strain in one direction to the strain in another. So what we should first do is to simplify the problem. So let's develop a coordinate system or an axis that we can use. So going to our schematic here, we will define the stress and strain in our transverse direction as our x direction, and our strain in the longitudinal direction as our z direction. So longitudinal and transverse just imply the direction of which our force is acting. So if our force is acting in the direction of our axes, then it's longitudinal. If it's perpendicular, then it's transverse. So the way to relate our longitudinal and transverse strain is using Poisson's ratio. So Poisson's ratio is equal to the negative strain in the x all over the strain in the z. So now let's take a step back. The problem asks for the initial length. So we can see from the schematic that our length is changing in the z direction and our diameter is changing in the x direction. So if we want the initial length, that means we need to solve for our strain in the z direction and then calculate our initial length. So we have two other parameters that we also need to find. In order to calculate our strain in the z, we need to calculate our strain in the x, and we need to find a way to calculate Poisson's ratio. So let's do the easy one first. Let's first calculate our strain in the x, because we know that that's going to be equal to the change in diameter all over our initial diameter, which can be simplified to our final diameter minus our initial diameter all over our initial diameter. The problem gives us both of our diameters, so we can simply plug in the values and compute the solution. So we can say that our final diameter is 20.025 millimeters minus 20 millimeters all over 20 millimeters. And this is going to equal a value of 1.25 times 10 to the minus 3. Again, we're dealing with strain, so it's unitless. So we've calculated our strain in the x. Now let's find a way to calculate Poisson's ratio. So the problem gives us both our shear modulus and our elastic modulus. So with those two, we can relate them using the shear modulus equation. So the shear modulus equation is equal to our Young's modulus divided by 2 times 1 plus our Poisson's ratio. So what we're going to do is plug in our values, and then we're going to calculate our Poisson's ratio by rearranging. So let's rearrange first. Our Poisson's ratio is equal to our Young's modulus divided by 2 times our shear modulus minus 1. So let's substitute our values. So we have 105 gigapascals divided by 2 times 39.7 gigapascals minus 1. And that's going to yield a value of approximately 0.322. It's important to note that Poisson's ratio is in fact a ratio and therefore it is unitless. So now that we have our Poisson's ratio and our strain in the x, we can simply rearrange our Poisson's ratio equation and calculate our strain in the z. So let's do so. So we can say our strain in the z is equal to our negative strain in the x divided by Poisson's ratio, and that's going to be simply negative 1.25 times 10 to the minus 3 divided by 0.322. And that's going to work out to a value of negative 3.88 times 10 to the minus 3. Again, unitless. So now we can do similar to what we did to problem 1. Define our strain in the longitudinal direction as our change in length over our initial length. So our strain in the z is equal to our change in length over our initial length, which is equal to our final length minus our initial length over our initial length. So now we need to rearrange for our initial length, and we're going to get our initial length is equal to our final length divided by 1 plus our strain in the z, and now we can simply substitute our values. So our final length, as defined in the problem, is 74.96 millimeters divided by 1 plus a negative 3.88 times 10 to the minus 3. And that's going to yield us a value of 75.25 millimeters. So finally, we can say that our initial length is equal to 75.25 millimeters. And that's going to be our solution to problem 2. Let's move on to problem 3. So problem 3 says a brass alloy is known to have a yield strength of 270 megapascals, a tensile strength of 380 megapascals, and an elastic modulus of 103 gigapascals. A cylindrical specimen of this alloy of 12.7 millimeters in diameter and 250 millimeters long is stressed in tension and found to elongate 7.6 millimeters. Based on the information given, is it possible to compute the magnitude of the load that is necessary to produce this change in length? If so, calculate the load. If not, explain why. So what we're dealing with here is a very conceptual question. And it's basically making us check if the test that we performed on this material is in the linear elastic region or beyond the point of yielding into the plastic deformation region. So if we look quickly at our stress strain curve, our point of yielding, sigma y, is defined as 275 megapascals. So if our strain value right here is our strain at yielding, if the strain that we calculated at our test is greater than our point of yielding, we are in the plastic deformation area. If we're less than, we are in the linear elastic region area. So in order to solve for the magnitude of the force that which is applied, we need to be in the linear elastic region so that we can use Hooke's law to convert between stress and strain and therefore calculate the magnitude of the load. However, if we are past the point of yielding into the plastic deformation area, which is here, plastic, elastic, then we have not enough information to calculate our initial force. So let's write down an inequality. So if our strain at our test conditions is less than our strain at yielding, then our deformation is elastic and we have enough information to solve this problem. So let's go ahead and calculate both and see if our inequality holds or not. So our strain at our test condition is equal to our change in length or our elongation divided by the initial length. So we're given the elongation of 7.6 millimeters and the initial length of 250 millimeters, and therefore we get a strain of 0.03. The last thing to do is calculate our strain at yielding. So if we're to the left of point of yielding, we are in the linear elastic region, and therefore we can use Hooke's law. So Hooke's law gives us our strain at yielding is equal to our stress at yielding divided by our Young's modulus, which is equal to 275 megapascals divided by 103 gigapascals. And make sure you convert the units so that they're equal. That'll give you a value of approximately 0.0027. So let's look at these values and with respect to our inequality. Our strain at yielding is less than our strain of our test conditions, and therefore we are in the plastic deformation area, and we don't have enough information to solve this problem. So we can conclude that because our inequality does not hold, we don't have enough information to solve this problem, and that's how we're going to conclude. That's the end of problem 3.